Okay, so this talk is going to be about generation, and in particular, neural language generation, but I'm going to first comment that when you look at the NLP literature collectively for a long time, the primary focus has been more on understanding as opposed to generation. And I think it's in part because we felt like we don't even know how to understand language quite right with computational models, and it's really hard to generate text when understanding has not been really solved. Nonetheless, there has been dramatic recent increase of interest in NLG, and that's in part because with deep neural networks, now we can generate much more fluent language than what was previously ever possible. So it's been a very exciting time the past few years, and there has been, as a result, also more industry interest on dialogues and conversational AI and so forth. So as you may have heard, 2 years ago, Amazon came up with this grand challenge known as Alexa Prize Challenge. The goal of this challenge was to build conversational models that can make an engaging and coherent conversation with people for more than 20 minutes. Within 1 year of time, I thought this challenge is just too hard. My guess was that maybe we can do 1 or 2 minutes, maybe 3. Turns out our winning system in the end was able to achieve more than 10 minutes. So we went to Las Vegas to receive the award. And this flying face is Noah Smith, who taught HMM earlier today. So then you might wonder, how did we do this? That sounds amazing. Well, sorry that I cannot tell you that it was amazing deep neural network architecture with reinforcement learning that did an amazing job. Instead, I mean, we wanted to do this, but we quickly realized that we probably should do something more like this, which is more traditional way of building dialogue systems that have different modules, and you have different types of statistical models and machine learning algorithms involved in different pieces, but we basically couldn't make it work using brute force more data, deeper neural networks, combined with reinforcement learning. So in this talk, I'm going to tell you about what does work well with neural network generation and why it doesn't work when it doesn't work, and then possible solutions and research path toward making something really working with neural networks, because we like neural networks. So before I go there, I'm going to briefly comment that there's something interesting going on with today's neural language generation. Before deep learning took off, generation models almost always started with a chain of understanding modules, like parsing and tagging and chunking and all that. Whereas today, they seem to rely less and less on understanding pipelines. And in addition to that, any significant improvement with parsing, tagging, coreference resolution, or question answering does not necessarily mean that suddenly generation quality will become better. So it's in part because what's been working really well recently tends to have this what's known as end-to-end model architecture that doesn't have a pipeline inside, and it just works better that way. So we started losing understanding pipelines as a result. In particular, there are many modeling variants here, but they tend to be based on some sort of encoder-decoder or sequence-to-sequence architecture with some sort of attention mechanisms. And they, in the end, all rely on some sort of language models under the hood. So it can either be conditional models, in which case, like sequence-to-sequence architecture, where given a context, you want to generate a sequence of words that can be a sentence or a paragraph, which then boils down to generating one word at a time, given all the previous words and the context. The generative models, in particular the language models, are in the end in a similar form, in the sense when we rewrite the joint probability of a sequence, we end up having this probability of predicting the next word given all the previous words. And this particular modeling tends to work really well for a variety of things. So it's almost like a universal model that's useful for a variety of tasks like machine translation, speech recognition, image captioning, and so forth. However, hinted at the beginning of this talk, neural generation can be quite brittle. So for the Alexa challenge, nobody could really make it work. And in addition to that, recent work by Weissman et al. Reported that when doing data-to-text generation, even templated baselines, which are boring, unfortunately, can do better than neural networks. So you might wonder, how bad are they, though? So I'm going to show you an example when neural network goes awry. And in order to go awry, there's no adversary necessary. So when we sample one sentence out of a language model that has particular architecture known as GRU, the details are not very important, but it's trained on a lot of data, in particular hotel reviews that has 350 million words. So that's plenty of data, and language model quality better be good when trained on that much of data. So this is the first sentence that was sampled. All in all, I would highly recommend this hotel to anyone who wants to be in the heart of the action. It sounds nice. And then it goes, and want to be in the heart of the action. If you want to be in the heart of the action, this is not the place for you. However, if you want to be in the middle of the action, this is the place to be. Very funny. So what's wrong with this, apart from being funny? Well, first of all, there are a lot of repetitions. It loops around. It's a known problem with neural language generation. And then it tends to contradict itself very easily. And in addition to that, it tends to generate text that is generic, bland, boring, and so forth. Not a lot of details about the hotel. It just says a lot of very high-level things that are likely to be safe. So that's just strange, because we certainly gave neural networks only natural language. Why unnatural language comes out of it? Why? Is it because we didn't have enough depth, or not enough data, or not enough GPUs? Well, I'm going to argue that even with more depth, more data, more GPUs, we probably are not going to be able to have a neural network that can generate long-term coherent text. And it may be that we really need a different game plan. So I'm going to claim that there are at least two limitations of language models that seem more critical to address for generation. A, language models are passive learners. If you think about how we learn to write, we certainly learn to write by practicing and get feedback, and you try to revise and so forth, and then your writing skills improve. But if you ever just read text, a lot of books, a lot of papers, but you never ever write ever, it's unlikely that your first text will be very good. So even RNNs perhaps need to practice writing. In addition to that, language models are, in the end, surface pattern learners. So they don't really have the idea about how the world works, the latent processes behind how people understand language and generate language. So there are at least two these problems. I'm going to first address the first problem. So it's a paper to appear at ACL pretty soon, next month. And so we began with this text and summarized symptoms. The problems are that goes into repetition loop, can easily contradict itself, and in general, too generic and boring. So why this is happening? Well, there are a number of different explanations to it. We think that, first of all, learning objective isn't quite right. People don't necessarily write to maximize the probability of the next token. There tends to be a lot more complex reasoning behind it. And in addition to that, with current architecture, long context gets easily ignored. It's also explained as explanation away effect by a recent work. And then also, the inductive bias may not be strong enough in the current architectures. for learning discourse structure or discourse coherence. So then we propose the following framework where we just let RNNs practice writing. So let them write. And then we create a committee of critics to compare what RNNs do, recurrent neural networks do, to human-generated text so that we give some feedback to the baseline, original neural network generator that way. So in particular, the discriminators or critics are inspired by Grice's maxims that consists of quantity-quality relation and manner, which we roughly approximate as relevance model, style model, repetition model, and entailment model. And we are going to begin with relevance model. And here what we want to address is that given a context like we had an inner room and it was quiet, we don't want language model to continue this way, that the staff was very friendly, helpful, and polite. It's not so bad, but we wish that it's more relevant to the context. So for example, we wish to generate, there was a little noise from the street, but nothing that bothered us. So this is actual system output, named as learning to write. So in order to do that, we use a neural network architecture known as convolutional neural network that can compare the initial context with the potential continuation. And we train to optimize that discriminator to reduce the ranking loss. So that's roughly how it works. And then in the case of a style module, what it's trying to address is the following. So even without looking at the context, oftentimes just by looking at the machine text, we can see some things a little bit different from human text. So machine text might look like it's time to go. So this is from Toronto Book Corpus. It's an amateur novels, and based on that neural network, trained on Toronto Book Corpus can generate some novel-like sentences as follows. It's time to go, the woman said. It's time to go. She turned back to the others. I will be back in a moment. She nodded. So it's not bad. It's fairly simple sentences. If you keep generating sample more sentences, they tend to be a little bit generic compared to what humans do. So what we want to achieve is something like this. They didn't speak at all. Instead, they stood staring at each other in the middle of the night. It was like watching a movie. It felt like an eternity, since the sky above them had been lit up like a Christmas tree. The air around them seemed to move and breathe. So this is an actual system output, and how did we get this is by doing the following. So we use the same convolutional architecture as before, but this time we just look at the human text and the machine text and compare the ranking between the two instead of looking at the context at all. So just by looking at the style of language, can we say something about whether it's machine-like or human-like? And moving on, the repetition module is trying to address the following problem. So a language model might say, he was dressed in a white t-shirt, blue jeans, and a black t-shirt. So it tends to stay on topic by repeating some words and phrases in a funny way. And we wish instead to say something like, his eyes were a shade darker and the hair on the back of his neck stood up, making him look like a ghost. So that looks nicer. And in order to address that, we trained recurrent neural network-based discriminators to differentiate between language model, machine text, against the human text, and conditioning only on this similarity between the two. So this is one way to address the repetition. Some of the prior work simply do not allow any trigram or ngram from repeating at all, which is a somewhat crude measure, whereas in our case, we parameterize the similarity so that we learn how to avoid repetition in a more natural way, because sometimes we do want to repeat some words or phrases because that's necessary. So finally, we have Entailment Module, which aims to address the following problem. So let's just say the context is I loved the in-hotel restaurant. And given that, we don't want to say that the next sentence, if the next sentence is there was an in-hotel restaurant, it doesn't conflict, but on the other hand, it's the same information twice. So when we say something that obviously entails from the previous sentence, that's not necessarily a desired effect. Of course, we don't want to contradict either. So we don't want to say the closest restaurant was 10 miles away. That just doesn't make sense. So what we do want is something neither entailment or contradiction. So it's a bit expensive, but well worth the price. So that's the desired way of writing coherent text. And so in very recent work, in fact, this year's work, this sort of entailment module has been shown to be useful for summarization tasks. In that case, they were comparing input and the output to check whether output is entailed by the input, whereas in our case, we don't compare between input and output. It's more about whether within the output, whether different sentences are entailed or contradicted from previous sentences or not. So the details are a little bit different. So for that, we use a well-known data set known as Stanford NRI and multi-NRI data sets that have this three-way classification labels about whether something is entailment or contradiction or neutral, and use that to determine whether we have undesirable situation or not. So having all of this, in the end, what we do is that we just put together all these discriminators to collaborate with the original recurrent neural network generators so that they do cooperative writing. And so in this regard, we are now making natural language understanding more integrated directly into generation as opposed to just doing this generation business without understanding pipeline at all. I do think that the generators in general, we do need to somehow model understanding problems better. It's not the case that we actually solved understanding problems, but somehow we need to find a better way of integrating understanding modules to generation. And unlike the more commonly or conventionally studied language understanding problems, in our case, we don't look at formal linguistic annotations, but rather look at discourse patterns that are rather indirectly measured by comparing machine text with human text. So in order to do this cooperative writing, what we do is when we do beam search or finding the k-best sequences, you learned how to find the one best sequence today. You can immediately extend it to find the k-best sequences. And from that on, using language models, we momentarily consider k-squared potential continuation, what word to produce next. And usually out of this, we choose just top k again. But in our work, we re-rank this using all these discriminators scoring functions so that we reorder what best k should be differently using the discriminators. And then we sample out of that k-best proportional to the scores, collective scores. So, yes. Yes. So it's discrete decisions about what word we might want to use. Not sure how many of you have learned neural language models already, but with neural language models, you also need to maintain the hidden state vectors that correspond to a particular decision that you just made. So in that regard, you're keeping both the discrete decisions as well as the continuous representations momentarily, and then you go from there. It's the letter. So it's the letter in the sense, in order to consider the next word, we need to momentarily decide what the previous generation may have been. We consider multiple options, but at each point in time, you consider one discrete decisions. And then there will be actually, it's a little bit more detailed than necessary, but there will be discrete k squared. Actually, it's more like k by the vocab size momentarily, which I'm like hiding here. But maybe we can take it offline. It seems to take a little bit more effort. So what we do in the end is not entirely new. It's a model known as product of experts, invented a while ago, in which we replace the decoding objective function from neural language models by a weighted combination of the base recurrent neural network models as well as a collection of discriminators scores. So that's what we do, and we learn the mixture coefficients among all these discriminators in order to learn how to do the best generation. So as far as the data sets, we considered Toronto book corpus as well as TripAdvisor hotel reviews. And then input-output setup in our particular work is that we use 5 sentences as context, and then we aim to generate the next 5 sentences. And we experiment with a bunch of baselines, such as adaptive language models are one of the, from our experiments, it performed much better than just using vanilla LSTMs or GRUs or RNNs. And then cache-based language models and sequence-to-sequence architecture, as well as more recent sequence GANs. And we found that when we use ngram-based evaluation measures, such as Blue, Rouge, Meteor, which have been used in machine translation or summarization, we do perform a little bit better than all the other baselines. However, these measures are not very meaningful because they tend to just look at surface pattern matching. So it's not really true quality of the generated text, which means we should really do human evaluation. So when we compare our machine text with any of the baselines shown one at a time, we found that humans preferred our learning to write text better than any of these baselines with higher frequency. So that's good, and this is on book corpus. And we can also do human evaluation on different aspects of writing. So for example, are we repeating ourselves, contradicting ourselves, and so forth. And again, we do better than other methods. But however, our performance, relative performance, is weakest for the entailment model. And that's because the kind of entailment that the existing data set captures are based on human text, whereas in our case, our model should operate on machine text. And there's a bit of a domain switch because of that. And that's why entailment model didn't help as much as other cases. So let's see more examples of how our model behaves compared to other strong baselines. So compared to the sequence-to-sequence architecture, so these are baseline, the vanilla language models that have sequence-to-sequence architecture. It might generate something like she looks up at the sky, the light shines brighter, the light flickers, the light flickers, the light flickers. Always poetic. But ours can do better. So for example, she's staring at the floor. She's shaking her head in wonder. What do you mean? Don't you know what it's like in your dreams? Nora asks. So let's look at another pair. This time we're comparing against the sequence GANs. We are going to leave. When he ended up here, he was here. Not really. It was ... It was a hard question. So compared to that, we generate. There was only one way to find out. The door swung open. Gregor stood in the middle of the room staring up at the ceiling. His eyes were wide and his breathing was shallow. What's happening? So I think ours is better. So here's a quiz for you. Now I'm going to read hotel review, and you're going to tell me whether it's a human written or machine written. Super tricky. So it goes like this. Our maid service was prompt and efficient. The beds weren't made up until late afternoon, but we had plenty of towels, etc. Also, there's a free shuttle to and from Walt Disney World, Universal or Orlando Premium outlets. Plus, there's a 24-hour Walgreens nearby to stock up on snacks for the room, as well as an internet cafe that's open 24 hours a day, which made it convenient for us. I'd recommend this property to families and business travelers who don't mind spending a bit more money, but would probably stay somewhere else next time. It's very nice with friendly staff, good pool facilities, and excellent on-site dining options. However, the prices at the parks are ridiculously inflated. So how many of you think this is a machine text? How many of you think this is a human text? Yeah, so why did you think this is a machine text? Repetitions. A bit of a control. All right, so yeah, you're right. Collectively, you're right that this is a machine text, but I think it's pretty good compared to how it used to be. Style is not right? Yeah. I agree. So I think it's a pretty good, it's like subtly awkward here and there, but you have to really focus to see them. And some humans write worse than this, so. All right, so did we solve everything now? No. So we addressed the first problem to some degree, but we have still a long way to go. In particular, language models are surface learners. Even with learning to write framework, they still are. They don't really have much idea about how the world works. And I think in order to really address this challenge, we may need to look at this more seriously. So, but that said, going back to this question of whether we are reaching human level performance or not, there has been a lot of sort of like media coverage that says superhuman performance on object recognition, image captioning, machine translation, and speech recognition, and even reading comprehension, as if we solved all of this. And it's true that we sometimes do better than humans on a particular data set. However, what's amazing is that common to all these success cases are that they use a lot of data and then sufficiently large networks. And so these two together seems to be what works well for a lot of things, potentially for every task possible in the world, which may or may not be the case. So I'm going to point out that somehow nobody reports a superhuman performance on making a conversation or summarizing a document or composing and replying to emails on behalf of you or identifying fake news, even though for any of these domains or tasks, there are a ton of data out there, at least for major industry companies, and they do have a lot of GPUs, so they should be able to train very large network on a lot of data. So why is it that nobody reports a superhuman performance on these tasks? And in addition to that, what about this robustness issue that whenever you give unfamiliar or out of a domain or adversarial examples to any of the successful neural networks, they still behave very strangely and making very easy mistakes. So I'm going to argue that basically these are two entirely different types of tasks that we're looking at. The kind of a task in type 1 case can be solved, or we can make things work quite well based on shallow understanding. And this is the case when there's a strong alignment between the input and the output. Surface pattern matching can go very far. So for example, if you were to translate bananas are green in English sentence into a Polish sentence, banana są zielone, neural networks are very good at learning word-to-word or phrase-to-phrase alignments to learn to translate language. But that doesn't mean that neural networks can now have a conversation with you. So in the case of type 2 task, for example, conversation, when I say bananas are green, you might say, no, they're not. Or you might say, they're not ripe. In order to be able to generate words like not or ripe, which were not in the input sentence, we do need to be able to do different types of learning, such as abstraction or reasoning. And if you try to learn this sort of input-output pairings based on traditional machine learning algorithms that just looks at input-output pairings, it's really confusing to the machine learning algorithms because there's not clear alignment to learn about. And so this is the case when we can no longer ignore the fact that the way humans use language and the way we understand, generate text is really based on rich context about how the world works, which includes common sense knowledge. So in order to address tasks in this bucket, we really need to start thinking about how we could potentially model the world that goes beyond just language. To make a clearer point about how it's important that we need world knowledge to read between the lines, which is the primary difference between machine understanding of language and human understanding of language. Let's consider this news headline. This is an actual news headline, cheeseburger stabbing. And if you try to parse it with a state-of-the-art parser, it's going to tell you that cheeseburger is a noun modifying another noun, stabbing. Depending on what parser you use, it might say this is a verb. In any case, knowing this relation doesn't really tell you whether this headline means someone stabbed a cheeseburger, or a cheeseburger stabbed someone, or a cheeseburger stabbed another cheeseburger, or someone stabbed someone else over a cheeseburger fight. So you know trivially what must have been the correct meaning of this news headline, because in addition to understanding what are in the sentence, you can immediately see that fill in the missing information that there must have been two people involved in this event to make it a news headline. So it's really about what's not said. And in order to do this sort of reasoning, we need different types of common sense knowledge. The physical common sense is that it's not possible to stab someone using a cheeseburger because it's too soft. And as far as social common sense, it's not very nice to stab someone. But it's okay to stab a cheeseburger. You're not going to appear in a news headline by stabbing a cheeseburger. So stabbing someone is immoral. That's part of our social common sense. So speaking of knowledge, it's in fact, NLP research has focused a lot on learning encyclopedic knowledge, such as who is the president of which country and born in what year, under this branch of research known as information extraction. And so there has been a lot of attention to knowledge in general in NLP research. However, encyclopedic knowledge is only part of the knowledge. And as a matter of fact, I can make a fairly okay conversation day to day without really remembering who was born in what year. So the common sense knowledge is what we really need. So naive physics knowledge as well as the social norms that we just looked at. Now, as far as the common sense knowledge goes, if you look up ACL Anthology, which is the repository of NLP conference papers and journal, most of the papers came from either 80s or most of them came from like early 80s or sometime then, and then a little bit from the past few years. It's in part because in early AI, people were excited about common sense, but they had miserable failures, so they decided that it's just silly to even think about it, so we should work on something more serious, not this. But eventually, I think young people just forget about the history, and they go back to the question of common sense again. So we started seeing new data set challenges for which models based on surface patterns do not seem to operate as well. So brute force large-scale training does not seem as promising on this type of challenges compared to where they have success today. So I'm going to then talk about our work presented at iClear this year about simulating action dynamics with neural process networks. And as a little motivation of this work, I'm going to start by our previous work known as neural checklist models for generating recipes. Given input title, recipe title, like a deep-fried cauliflower, and then a bunch of ingredients that you have in the kitchen, the task was to generate long text, which is just entire recipe on its own. And we were able to compose a model that does fairly reasonable job. So here it goes. Wash and dry the cauliflower, heat the oil in a skillet, and fry the sauce until they are golden brown. Drain on paper towels and add the sauce to the sauce and mix well. Serve hot or cold. So it's just slightly funny, but in some sense it looks reasonable, but it's still not quite right. So what's not right? Huh? Where's the pepper? What else? Yeah, well, just fry the sauce to the sauce. That sounds weird. What else? Right, yeah. We forgot to cook the cauliflower. So, by the way, the model works really well for other types of recipes, but I'm showing you more of a failure case, and the model tends to fail when the context is unfamiliar. So I've never had a deep-fried cauliflower before myself. This recipe do not appear very often. So whenever the context is less familiar, RNNs tend to fail more easily. When I presented this work at Harvard University a while ago, a student asked me whether RNNs are a mouth without a brain, and I had to agree with her. So as a result, I really wanted to address this problem that we somehow need to think about how we could model, the kind of causality, the common sense knowledge about maybe starting with the kitchen in order to be more robust against the previously unseen situations, which has something to do with AI safety. And in fact, very recently, also Julia Paul made this comment that machine learning models today seem to be really strong with associative learning, pattern learning. However, not as good about causality. So can we somehow better handle this? So repeating myself several times by now, RNNs tend to be surface pattern learners. And it's not able to really reason about the obvious but unspoken things about language understanding. So when I say fried tofu in the pan, you can immediately know that the location of tofu must be in the pan now, and the temperature of the tofu will arise. But it's not written in this sentence, so today's parsers are not going to know any of this. So can we somehow create this sort of a mental simulation that we seem to be doing, which was also discussed by previous literature in cognitive science and psychology, that we seem to have a mental physical engine or mental simulation engines in order to reason about previously unseen situations. So now the desired aspects of the modeling then is to understand the text by simulation. In particular, we wish that we simulate the causal effects implied by the input text, focusing on not only what's said, but also what's not said but implied. That abstracts away from the surface strings, and in fact, we are not the first to do this. There have been some recent neural network architecture that addresses some aspect of this sort of simulation effect. And we are proposing a new approach that can handle the causal effects of actions better. And this contrasts with a more conventional way of understanding text by labeling, in particular labeling syntactic and semantic categories of surface words, which are very important aspect of language understanding. But since we are doing much better job here, now may be a good time to also think about the simulation aspect of understanding. So with that in mind, we proposed this architecture that we named as neural process networks. And I understand that some of you may have not learned neural networks just yet, so just consider this as more intuitive, high-level story about what may or may not be possible today. So it's going to start with a language model-like architecture. In our case, it's a GRU that reasons a sentence. And then there's going to be a neural network architecture that's going to reason about what actions to execute to which entities, and then apply that action to those entities, which is basically simulation, such that the resulting entity states should be able to, the model should be able to reason about the causal effects of the actions with respect to different dimension of the changes, such as location, temperature, and so forth. So a little bit more detail about each of these components. It starts with the action selector. And before we begin, we have this special memory block that's basically verb representation or action representation. It's just a stacked vectors, neural vectors. And we select which actions to apply attentively by composing potentially different verbs into composed verb representation. So for example, when we see a word like a fry here, contextually, when people say fry, they sometimes mean fry plus actually moving the location of the ingredients first to the pan and then fry. So we might, for example, have maybe 75% of a fry embedding combined with 25% of a put embedding, however the model wants to do. And then having done that, we need to now select to which entities we apply that action. So similar as before, we have a special memory block that stores different entities in the kitchen. And then we are going to select what entities to apply that action to attentively as before. But in addition to that, there's a little bit more details. Sometimes there's a previous sentence that introduced some entities. In this case, previous sentence might have said, season tofu with salt and pepper. And then the current sentence says, fry that tofu in the pan. So here, the tofu really means that tofu plus salt and pepper, because now they are all together. So for that reason, we do this entity selection recurrently by feeding this selection through recurrent chain. And then finally, once we have both of these done, now it's time to do the cooking action without actually having the kitchen. So in order to do that, basically what we do is we take action embedding and then entity embedding and do some vector operations, because at the end of the day, this is just a neural network, which means everything is vector matrix operations. So we do that such that the resulting embedding, when we try to interpret what the result became of, it's going to be able to explain itself in natural language phrases, such as maybe location is now pan, temperature is now hot, and so forth. So that's the whole story. Once we have that, we actually need to update the entity storage with this new embedding so that the cooked results are being reflected in the memory somewhere. So that's the overall architecture. I know that it was a little bit dense, so let's move on. So the data set in our case was some bunch of cooking recipes, and we annotated only a small subset of them to use as a dev set and test set with a lot of low-level interpretation of what's happening to which entity in what way. But otherwise, this is going to be a situation where we have to learn from distant supervision, because we cannot learn from actual simulation environment. alpha 0, or there have been other types of successful case of reinforcement learning with the simulation environment. However, it works only when there's a simulation environment, and we don't have a simulation environment for kitchen or social dynamics for the matter. So what about those cases when we don't have a simulation environment? Well, we could do more like distant supervision. We certainly cannot do very, very low-level annotations in an extremely large scale because that annotation is too expensive in general. So that's what we do. Briefly, more concretely, what we do is we have a bunch of loosely labeled based on heuristics that we feed as component-wise loss function together with other function. So for evaluation, we've done both intrinsic and extrinsic evaluation. Intrinsic evaluation is basically inspecting whether the entity tracking is done correctly, and then extrinsic evaluation is to see whether this architecture is any useful for some downstream applications like text generation. So starting with the first one, we've done a bunch of annotation, but it boils down to two types of a task. One is selecting the entities correctly, and then the next task is depending on the first task being done right, but in any case, it's about whether you predict the causal effects correctly as well. So for that, the quick conclusion is that based on simple language models, which do not have external memory architecture for tracking dynamic entities, also which do not have explicit modeling of action causality, they perform about this much of an F-score. With recurrent entity networks, which do have external memory of dynamic entities, but that doesn't have explicit modeling of action causality, the performance improves. However, when we do both external memory for entities as well as external action causal modeling, then we can improve the performance further up. So for the extrinsic case, this is when we use this memory architecture that simulates different actions that happens in a story or narrative, and then use that in order to enrich the context for neural text generation. Then we were able to show that we can improve performance based on a variety of different measures of text generation. So to briefly summarize, this work was to explore this new direction of understanding text by simulation, where the focus is really about abstracting away from the surface patterns and try to simulate the causal effects implied by text, but not in text, which can complement the other direction of research that has been done a lot more often. So now I'm going to have a bit of a concluding remarks. So going back to our the talk plan today, I was talking about two limitations of natural language generation today due to the limitation of language models today. Somehow, natural language understanding research today tends to focus on understanding only natural language, whereas generation seems to require understanding both machine language as well as human language, because it needs to be able to inspect the generation that it's doing. And in addition to that, they're generally passive learners, and they might need different mechanisms to improve their sampling algorithms. And so going forward, slightly broadening the scope, I'm going to briefly discuss what research directions may be exciting in the field. So in some sense, the neural process network that I just talked about is the research that focuses on neural network architectures. There's been very interesting debate between Yan-Lu Kun and Chris Manning about whether we want to have innate structure or not. And I am on the side of having innate structure for sure. However, it seems that in the NLP community, we focused more on the structure of a sentence, especially using explicit linguistic structure, focusing on words that are present in a sentence, whereas we seem to need to do more of these other types of a structure, such as context and the world model, in order to address this question of how do we handle this implicit and latent processes that generates the language and be able to read between the lines. And then in addition to that, it's unlikely that this alone will really solve every NLU and NLG challenges. So perhaps we also want to think about the formalism for modeling common sense knowledge using language as sort of representation scaffoldings. And for that, I'm going to make a brief comment about how I was once told not to use the word common sense because then nobody will take me seriously. But then I realized that that's just irrational because past failures are inconclusive when it was based on weak computing power, not much of data, no crowdsourcing, not as strong computational models or algorithms, and well, it was not done by NLP people, and I think we can do better when we think about language more carefully. So in recent years, we've been exploring that idea for both the physical common sense knowledge, which can be really useful for addressing zero-shot or few-shot learning cases, especially for multimodal domains such as language and vision or language and robotics, but also social common sense knowledge, especially focusing on script knowledge of events and stories, and also looking at naive psychology of people and so forth. And going forward, I think there's a lot of opportunities for thinking about new challenge data sets as well as unified representation formalisms and models for common sense knowledge. So as a very brief preview of an ACL paper coming up that we have this paper about event to mind, Commonsense Inference, together with Noah Smith here. So when given an event description like here, person X cooks Thanksgiving dinner, we can trivially reason that, well, probably the intent of that person is to impress their family. The likely reaction after the event is that they feel tired or feel sense of belonging. And probably other people are impressed by that or thankful for the nice dinner. So we do this sort of reasoning fairly trivially, and it seems that we can explain all this in natural language, so why not build a model that does do that? So given the textual description of an event, what we do here is to generate all these intent and emotional reactions of different event participants in natural language. So we have a new crowdsourced data set coming up together with the model, and a companion paper about naive psychology of story characters, but I'm going to just skip this for, in order to finish the talk very soon. So lastly, I want to point out that there's been a lot of concerns about AI being scary, and I think we can address that concerns in part by creating technologies that can do positive things in the society. So, for example, detecting fake news seems really, really important today, which also requires reading between the lines, among other things. And also correcting unwanted biases in language that might go against underrepresented groups. So there's a ton of opportunity here. And also, I think we could make our NLP models to be more interactive than before, especially addressing dialogues and social conversations, because that immediately makes our models more useful for grounded settings with robots, for example. And finally, it seems that now that neural generation starts working much better than before, there's a lot of opportunity for doing something creative here. So I'm going to end with a sonnet that was written by a machine. The input for the machine was the title Turing, and it wrote the following: creating some electric slot machine of hearing those familiar voices say, Awake behind an empty picture mean the window is open over LNK. Consider me a regular expression or maybe something very quickly typed. And I forget about an old obsession, 100,000 of people getting hyped. Become the biggest part of my computer and take another journey down the road, or set a balance on a minor scooter, or even matter whose Enigma code. And music takes control of all the means surrounded by a world of strange machines. So this was the best system in the Dartmouth Turing Test Challenge in 2016. However, we couldn't fool anybody. Thank you.
Thank you for the amazing talk. And I have I have many questions, but we have time for a couple of questions. So one is more technical, another one is more abstract. So the technical one is like you were comparing your model with the SIGGAN, and they use policy gradients when multicolor search for training, right? And like as far as I know, like there are some other ways like using reinforcement methods like actor critic methods. So what are you using in your model?
So we use their code and just to follow what they did, which is based on reinforcement learning. I would like to, since you asked the great question, I would like to make a general comment about the problems with the GANs as is today. Oftentimes the generators are not strong enough to begin with. So it's very easy for discriminators to tell apart the differences between machine text and human text. So when generators are not very good, they cannot really go very far between generator and discriminators. What we propose to do with learning to write framework, which can then also be framed with the GANs on top, is that let's make generator as strong as possible. And in order to do that, we do need a different architecture that can look at discourse structure better, because it seems that simple sequential patterns are only strong for sentence level generation, but starts breaking apart really fast with paragraph generation. So in order to handle paragraph generation better, we need to make generator better. And in order to do that, one way to do that may be learning to write. There may be other ways of doing it. Some of you might come up with that, but yeah, that's sort of the insight.
Thanks. And another question emerges. So if you do a very strong generator, for instance, if I do like controlled generator, it will have some prior knowledge from like, I don't know, I generate some forms based on some controlled like generators, right? And then I will use it to train a discriminator. Is it like, there won't be any backward like connection back to generator anymore, right? Because we don't need to make it stronger. It's already like the best possible.
It may be good to iterate. I think it's a great idea to iterate. And in fact, we sort of wish that we do iterate, except that before ACL deadline, it seemed that we really have time for just one iteration. But I think there are a lot of other things we could potentially do so that they become better.
Okay, thanks. Another question is a like more abstract one. So this is like about, you were saying that there are not many that papers about conversation or summaries and everything where you have highly unpredictable events, right? Those black swans which appears from nowhere and then like they are about everything. So you have huge data sets with all average data what you have, but you never will like, well, with the poetry it's the same. You will never create anything new with this. So all the time you will be learning from the thing which already was written by someone. Even if you like combine them together, those combinations might look interesting because just we humans read them and we see something interesting in that. And like that's a question like, is it interesting just because of our mind? Like we see it's there. So the thing is like, how do you think? Is there any way to generate, to make those neural networks able someday, somehow, to work with highly unpredictable events? Or it's just never possible and we need to forget about neural networks?
So let's not forget about neural networks. That's a short answer. But let's just see whether I understood your question. So are you concerned that the text generated by neural networks may have been a plagiarism of what humans wrote before? Yes, no. I wasn't sure if I understood your question.
So actually, I forgot already what you asked.
So it seems that one of your concerns that you described was whether machine text is based on, in the end, the human text, which means maybe machines are not really creating anything interesting. Maybe it's repeating what humans said in the past.
Yeah.
Okay, so that's not the case, especially with the sonnet. Nobody wrote anything like this before as a human. It's impossible to repeat what humans said as is more than a few ngrams in our study due to the fact that in this particular work, we intersect recurrent neural networks with the finite state automata of sonnets. And when you have that much of a constraints, it just doesn't allow the model to repeat what it's seen before, but it has to create something new. And similarly, with our learning to write framework, first of all, recurrent neural networks are not able to really memorize and reproduce what people said exactly as before, given how it's able to repeat strange, create strange new repetitions that no human has done before. But in addition to that, even with the learning to write framework, because in the end, the generation is done by only re-ranking of the potential next words, those discriminators are not able to reconstruct what someone else wrote in the past. It's all operating based on new context that it hasn't seen before. It's just the framework doesn't allow to reproduce a sentence or paragraph as is.
So you use the fragility of like recurrent networks, like this weak point, as a strong thing, right?
Yeah, it's a weak point is a strong thing.
Yeah, that's a great idea. Yeah. Thank you very much. I will ask more questions after because we run out of time.
Thank you very much for the interesting talk. I have a question regarding comparing your approach with other approaches which are existing. So I read this paper, go to the point, summarizing with pointer generator networks from those guys from Stanford University, Google Brain, and so on. So have you thought about comparing your system with this system? This is the first thing. And the second thing that I wondered whether such systems are practical to be used in industry, or they are just like, academic work, which needs some more.
Great. So first of all, the pointer network is sort of, the cache network is a little bit different from pointer. The pointer is a little bit better for summarization setting, but since we are doing neural language model in the end, in this, the first segment of the talk, we do the cache neural language model. It's very similar. It's basically pointing to some words that happened before, which allows you to stay on topic and be more coherent as a result. So we did compare against the cache LM. Point network doesn't make as much sense to be used directly as language model, however. But this is very similar in concept. Your second question about, are these just purely academic work or has relevance to industry? I would argue that as far as application goes, probably it's relevant to industry since there has been increasing interest in creating conversational AI systems and also a lot of startup companies on this topic as well. The semantic scholar, for example, created by some NLP people got acquired by Microsoft recently, which is another example of a dialogue system. So there has been a lot of improvement which allows people to start thinking about industry applications. However, what works today tends to be more either goal-oriented or domain-specific or short-term interactions. And in order to lift that practical limitations we do need to do more academic research simultaneously. So that's where we are today. But I think a lot will change very quickly within the next few years, given how much of exciting advancements we've seen so far.
So what's your opinion regarding the existing common sense knowledge bases? So what are the limitations?
Yes, so that's another really great question, because in fact there has been some common sense repositories like OpenPsych and ConceptNet, among others. So what happened with them? So I will say that first of all, those existing resources tended to focus more on taxonomic knowledge, like a bird is a kind of animal, penguin is kind of a bird, that's sort of a taxonomic knowledge, as well as very object-centric knowledge, like skies are blue and birds can fly and so forth. But they didn't focus as much on this sort of reasoning knowledge where you see a context, you can anticipate what might happen before and after, causal effects of different actions and events in people's life. And in the end, common sense is essentially about the ability to anticipate what may be trivially true in terms of probability distribution. So what we propose to focus more on going forward is A, to create resources that addresses this sort of reasoning knowledge, and B, to build robust representation of such knowledge, which currently we are relying heavily on neural representations, so that it can be integrated readily in some other downstream models. So these things have not been properly tried yet, so we should try before we conclude that there's no hope with common sense.
Thank you very much for the really interesting talk. To follow up a little bit on the common sense thing, what do you think about trying to infer some kind of common sense from extra-linguistic information, so some kind of grounding, maybe video processing, because this is something that I also think is I know it's hard to implement, but it's kind of natural to think about it because this is how humans are inferring a lot of the common sense information.
Absolutely. So that's a really great question. And in fact, we tried doing that like maybe 3 years ago or 2 years ago. And we learned that, for example, dogs are usually larger than cats by looking at a lot of images of dogs and cats. And then we also learned that elephants are much bigger than bananas by looking at lots of images. And then I realized that not only NLP has not been solved, computer vision has not been solved either. So I can see size with some approximate depth processing and size processing. However, it's really hard to see other types of physical knowledge like relative strength of the material or relative flexibility of the material, relative speed. These things are visible to human eyes, but not really to computer vision today. Videos should have some knowledge about relative speed, yes, except that it's very, very computationally heavy. So it seems really hard to acquire all that knowledge from images and videos only. However, still it's a really good idea to combine all the different knowledge sources. Now, speaking of all this relative physical knowledge, we had another paper that looked at language to focus on that sort of a relative physical knowledge, known as verb physics, presented, I think, in 2017 at ACL, in which we realized that when people, although people don't say that my house is bigger than me, because of course my house is bigger than me. So if you Google that, you cannot really learn it because nobody says that. But I do say that I entered my house and I exited from my house, which is only possible if I'm much smaller than my house. So you can then start reasoning about all these implications of different actions that people take with respect to different objects. And we learned that it's possible to reverse engineer a bunch of physical knowledge that's not really visual to computer vision today by just looking at text in a more careful way with the probabilistic inference. No deep learning there.